Hello everyone. Today we are going to analyze this beam using slope deflection method. Before analyzing, let's see the slope deflection equations. In a continuous beam, let us consider a random span AB. For every span, there will be two slope deflection equations. These are the two slope deflection equations with respect to the span AB. In these equations, m of AB is the fixed end moment in the point A, m of BA is the fixed end moment in the point B, theta A and theta B are the slopes at A and B respectively, 6EI delta upon L square is the fixed end moment due to sinking of the support. In the given problem, there is nothing mentioned about the sinking or settlement of the supports. In this case, we can assume that there is no settlement or sinking in the supports of the given beam. So, the fixed end moment due to sinking will be 0. So, when we make slope deflection equations, we don't have to consider these terms. We had a brief introduction about slope deflection equations. Now, let us start analyzing this beam. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 45 kN acting at 2 meter from the point A. In the span BC, we are having UDL 15 kN per meter acting for the full span. In the point A, we are having a fixed support. In the point B and in the point C, we are having hinged supports. Span AB is 6 meter long and span BC is 4 meter long. The moment of inertia for the span AB is 1.5 I. For the span BC, the moment of inertia is 2 I. In the slope deflection method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the point A, we are having fixed support. In the fixed support, there will be no slope. In the points B and C, we are having hinged supports. In the hinged support, we will have slope. So, the number of supports in which a slope can occur is 2. In the point B, we are having theta B, and in the point C, we are having theta C. So, in this problem, there are two unknowns, theta B and theta C. If we calculate these two unknowns, we can easily find the final moments. To find out these two unknowns, we need two equilibrium equations. Let's see how to make the equilibrium equations. Equilibrium equations can be made at the ends and joints of the beam. At the joints, the summation of the moments will be 0 and moment will be 0 at roller and hinge supported ends of the beams. So, in two ways, we can make the equilibrium equations. In the joints, the summation of the moments will be 0. Then we can look at the end conditions. In the fixed end, there will be a moment, so we can't make an equilibrium equation. In the hinged end, there will be no moment, so we can make an equilibrium equation. In the roller supported end also, there will be no movement. Here also we can make equilibrium equation. Let us apply these rules in the given beam and form the equilibrium equations. In this beam, first let us look at the ends. In the point A, we are having a fixed support. In the fixed support, there will be a movement, so we cannot make an equilibrium equation. In the point C, we are having a hinged support. In the hinged supported end, there will be no movement, only there will be vertical reaction. So MCB is equal to 0. This is our first equilibrium equation. The second equilibrium equation can be made in the joint. In this beam, we are having only one joint, that is the joint B. Here we can make the second equilibrium equation. In the joint, there will be two moments. One will be acting in the clockwise direction and another will be acting in the anti-clockwise direction. So one will be positive and another will be negative, but both of these moments will be having the same value. So when we add them, it will be 0 because one is positive and another is negative and both are same. So MBA plus MBC is equal to 0. This is our second equilibrium equation. In this beam, we have to calculate three moments. In the point A, we have to calculate MAB. In the point B, we have to calculate two moments, MBA and MBC. So totally three moments. Also, we have to find three reactions, RA, RB and RC. Now we are going to make the slope deflection equations. In the slope deflection equations, we have to find the fixed end moments. So first, let's find the fixed end moments. First, let us make the fixed end moments in the span AB. For making the fixed end moments, we have to assume every span as a separate fixed beam. You can see that I have made the span AB as a separate fixed beam. Now let's see the formulas to find out the fixed end moments. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load. That point load is not acting on the center, so we have to select this condition. The formulas for the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. In the span BC, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let's apply the formula and find out the fixed end moments. In the span AB, the point load is not acting on the center. We already saw the formulas. Let's apply the values inside the formulas. W is 45, A is 2, B is 4 and L is 6. After calculation, we are getting M of AB is equal to minus 40 kN meter and M of BA is equal to 20 kN meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments. Let us apply the values inside the formula. W is 15 and L is 4. After calculations, we are getting M of BC is equal to minus 20 kN meter and M of CB is equal to 20 kN meter. Now let us make the slope deflection equations in the span AB. We already know for every span there will be two slope deflection equations. In the span AB, the moment of inertia is 1.5i. So instead of I, we have to apply 1.5i in both of the equations. We have already calculated the fixed end moments. We can apply them. The length of the span is equal to 6 meter. We can apply. In the fixed supports, there will be no slope. In the point A, we are having a fixed support. So theta A will be 0. We can cut theta A and make it as 0. Finally, we have made two equations. Now let us make the slope deflection equations in the span BC. In the span BC, the moment of inertia is 2i. So instead of I, we have to apply 2i in both of the equations. We have already calculated the fixed end moments. We can apply them. The length of BC is 4 meter. We can apply that. In this equation, let us make the first equilibrium equation. We know that in the point C, there will be no movement. So MCB is equal to 0. For MCB, let us apply 0 and take this 20 on the right side. So it will be negative. So this is our first equilibrium equation. We have made one equilibrium equation, but we need two. We already know the second equilibrium equation can be made in the joint B. In the joint B, MBA plus MBC is equal to 0. We have already formed the slope deflection equations for MBA and MBC. We can apply them. After adding all of the values, we are getting the second equilibrium equation. Let us keep this equation as number 5. Finally, we have made two equilibrium equations. Now we can solve these two equations using the calculator. If you do not know how to solve two equations in the calculator, see the description below. There is a link. You can click the link and watch the video. How to solve two equations in the calculator. I have used the calculator and found the unknowns. I am getting Ea theta b is equal to 4 and Ea theta c is equal to minus 12. Now let us apply these two values in the slope deflection equations and find out the final moments. When we apply the value of Ea theta b in the equation number 1, we are getting MAB, which is equal to minus 38 kilonewton meter. When we apply the value of Ea theta b in the equation number 2, we are getting MBA, which is equal to 24 kilonewton meter. When we apply the values of Ea theta b and Ea theta c in the equation number 3, we are getting MBC, which is equal to minus 24 kilonewton meter. So in this beam, we have calculated all of the moments. No need to apply the values in the slope deflection equations for MCB because we already know it is 0. In this beam, we have calculated all of the moments. For MAB, we have got a negative value. That means it is acting in the anti-clockwise direction. For MBA, we have got a positive value. That means it is acting in the clockwise direction. For MBC, we have got a negative value. That means it is acting in the anti-clockwise direction. Now let us calculate the vertical reactions. First, I am going to take the span AB and find out the vertical reactions. In the span AB, we are having two moments, MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. So when we calculate the reactions, we have to consider these two moments. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive, and the distance is 6, so 6 RA. The point load 45 kN is acting towards the point B in the anti-clockwise direction, so it will be negative, and the distance is 4 meter, so minus 45 into 4. This movement is acting in the anti-clockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 32.33 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, we are having three vertical forces, RA, RB1 and 45. RA and RB1 are acting upwards, so both are positive. 45 is acting downwards, so it is negative. We have already calculated RA, which is 32.33. We can apply that. Finally, we are getting RB1 12.67 kN. Now, let us take the span BC and find out the reactions. In the span BC, we are having only one moment, MBC, which is acting in the anti-clockwise direction. In this span, first I am going to calculate RB2. For that I am going to take moment about C. In this case I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RB2 is acting towards the point C in the clockwise direction. So it is positive and the distance is 4 meter. So 4 RB2. The UDL is acting towards the point C in the anti-clockwise direction. So it will be negative. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 upon 2. The moment 24 is acting in the anti-clockwise direction. So it will be negative. Finally, we are getting RB2 is equal to 36 kN. Now let's apply this rule and find out RC. RB2 and RC are acting upwards, so they will be positive. 15 kN per meter is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. When we do that, we are getting 60. RB2 we have already calculated. We can apply that. Finally, we are getting RC, which is equal to 24 kN. In the point B, we have calculated the reaction 2 times. Let us add both of them. After adding, we are getting RB is equal to 48.67 kN. Now let us make the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A towards the point C. In this case, I am moving towards right hand side. Upward forces will be positive and downward forces will be negative. You can see the calculations here. Now let us make the shear force diagram. For the positive values, we have to draw the diagram above this line, and for the negative values, we have to draw below the line, and we have to mark as positive and negative. Now we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram, then we have to combine both of them to make bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. In the simply supported beam, if the point load is not acting on the center, we have to split the beam into two parts, A and B. The formula for the maximum bending moment under the load is WAB upon L. Here W is 45, A is 2, B is 4, L is 6. When we apply in the formula, we are getting 60 kN meter. If in the simply supported beam, UDL is acting for the full span, the formula for the maximum bending moment is WL square upon 8. Here W is 15, L is 4. When we apply in the formula, we are getting 30 kN meter. In the simply supported beam, we know that if the point load is acting, the bending moment diagram will be in the shape of a triangle. If UDL is acting, the bending moment diagram will be in the shape of a parabola. Now let's see how to make the end moment diagram. Using the end moments, we have to make this diagram. First, we have to draw these curves. MAB is acting in the anti-clockwise direction, MBA is acting in the clockwise direction, and MBC is acting in the anti-clockwise direction. Now we have to see the direction of the curve. All the three curves are indicating upwards, so the points will come above this line. Let us mark them, here 38 and here 24. In the point C, there is no movement, so here it is 0. Then we can connect. Even though we are having two movements in the point B, we have to make only one point because both of the arrows are indicating upwards. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the values are coming above the line. That is why it is negative. Now we can combine the free movement diagram and end movement diagram. Wherever they are acting alone, we have to mark the sign with the values. If they are acting together, we are not marking anything. We just keep the space empty. If you are very experienced, no need to make the free movement diagram and end movement diagram. You can make the bending moment diagram directly. Now we are going to end this session. Thank you for watching this video.